Okay, so we're going to look at titration curves now. So if you don't have your PowerPoint, please pull it out. And I'm going to just send everyone, so you will receive one as well. Class today. Please join class by using the link on the home page in class. And that should be good. Okay, so as I said, we're going to look at this titration curves again. So a titration curve is a curve that is obtained by plotting pH versus the acid or the base that we're using to titrate. So in this case, we're talking about acid-base titrations. So we either titrate an acid with a base or a base with an acid. For the titrations, we will need to have, let's say if this is an acid, here's an acid, let me just make it a little bit thicker. And therefore, this one will have to be the base. If we look at this in general, we can say that this is the titrant. And this one here is called the analyte. So this titrant and analyte are two terms that I would like you to be familiar with. Titrant is the substance that is in the burette and is being added. The analyte is the substance that is on the beaker and is being titrated. So the titration can be a base with an acid or an acid with a base. So in general, we use them that we don't use the terms acid or base, but we use the terms titrant, is the substance or the solution that we're adding, and analyte is the solution that we are analyzing for. And this requires measurement of volume from the burette and measurement of pH. So there are two readings here that are important. So you need to read the burette and you need to read the pH meter. So that way we can actually plot them, volume of the titrant added with respect to pH. So then we're getting what is called a titration curve. So this first example is an acid and a base, a strong acid, a strong base at titration. And this second example is an acid, which is a weak acid with a strong base. So again, it's very important that you be able to recognize acids and bases. Again, the 6 strong acids and the 6 strong bases are important for you to recognize. So anything that is an acid and is not one of those 6 is going to be weak. Okay, the other important thing is going to be the conjugate bases of the acids. So this one here is the acetate ion, CH3CO minus, which is the conjugate base of the weak acid, which is called acetic acid. So this is acetate and this is acetic acid. When you have a weak acid and a strong base, you can expect the end of the titration to be in the basic range. Why is that? Because when you look at this reaction, you are reacting an acid and a base, a strong base. And what you're forming is the salt. Remember when we talked about acid-base properties of salt, we talked about which are the parents of the salt. So the parents of the salt are going to be NaOH and acetic acid. And therefore, if you look at the nature of the acid, so that the acid is a weak acid and this is a strong base, which means that this salt is going to be basic. Because at the end of the titration, we only have the salt, all the acid and the base at the end point have been consumed. So the pH at the end point has to be the pH of just the salt. And since this salt is basic, we expect the pH to be greater than 7 for this titration. On the other hand, when we have a strong acid and a strong base, then we can expect neither one prevails and the salt is going to be neutral. And in that case, we expect the pH to be exactly 7. When it is not a strong acid and strong base, then we're going to have a point in the titration in which we're converting the acid to its conjugate base. So at the midpoint, that is when we have added half of the amount that we need to reach the endpoint, the concentration of acid and base are going to be the same. Why? Because at the midpoint, we have converted half of the acid into its conjugate base. And therefore, these concentrations are going to be the same, which means that this number is going to be 1. And being 1, the logarithm of 1 is 0, and therefore the pH is going to equal the pKa only at the midpoint. Okay, so here we have the two titrations. One is a weak acid and the other one is a strong acid. Strong acid is the red one, so this is strong. And therefore the midpoint is not relevant because we are producing we're producing a neutral salt and there's no equilibrium. If we have strong titration, so strong acid, strong base, the only thing that is going to be relevant is going to be the endpoint being at 7, pH 7. This is HCl and the titrant is NaOH, which is a strong base. So we have a strong base here being added and a strong acid, which is the analyte. And therefore, the endpoint is going to be neutral and pH of 7. Notice that for the blue line now, this is a weak acid. So this is a weak acid with a strong base. Weak acid, strong base. And in this case, then the endpoint is right here. And if you can see, let's see if we can do this. So it corresponds to a pH other than 7. So the pH here probably, I would say pH, oops, so we need to switch pens. So let me erase this, yes, okay. pH, I would say is about 8.8. And since the pH is 1.8, 8.8 is not 7, is not neutral, which means that the salt that is produced is basic, and that makes sense because this is the child, so to speak, of a strong base, with a weak acid, so the strong is going to prevail, and the strong is a base. So the salt solution, salt is basic. When that is the case, when you have a weak and a strong, then the midpoint here has another important, let me make it in green, important value, which is the pH here is going to be equal to the pKa of the acid. So by doing the titration and finding what the endpoint is, and let's say this is 10 milliliters, excuse me, 20 milliliters, the midpoint is going to be at 10, and therefore we trace a line up to 10 to the line and come back, we come in this direction towards the pH. We can read the pH at the midpoint, and that corresponds to the pKa. Okay, so those are the two important features of this type of titration. And there's going to be some questions on the Kahoot, so please, if you have questions, ask. So here we have a strong acid with a weak base to produce the salt. So the salt is going to have the feature of the strongest pairing, which is the HCl. So this is going to be an acidic salt, ammonium chloride. So we can expect then the equivalence point to have a pH which is going to be less than 7. Remember that less than 7 means acidic. At the midpoint, this one is equal to 1, and logarithm of 1 is equal to 0, so the pH equals to the pKa. So, oops. Okay, so here we have a titration of a weak base in red. And the midpoint is pH 9.25. And that is the pKa of the acid. If we want the pKb, since this is a base, we have to use the equation pKa plus pKb is equal to 14. Or we can use Ka times Kb is equal to Kw, or 10 to the negative 14. So this is a numerical, the straight numerical product. This is the logarithm of the equation at the bottom. We can use either equation, they're very same. So this is a base, and this is the pKa. So this is the pKa of the corresponding acid. So the pKa of, let me erase this part. This is the pKa of, not the base, but the conjugate acid, which is NH4. It's equal to 9.25. Not a very strong acid, because this is 10 to the Ka is going to be 10 to the minus 9. So not a very strong acid, but still an acid. So the midpoint here always gives us the pKa. If we want to switch to pKb, we need to use either of these two equations here. And then we did this exercise on the titration of HCl and sodium hypochlorite, and we solved for that. So we have this reaction here, and since the concentration is initial concentration is 0.05. We do this minus x plus x plus x. And we need to be conscious of the coefficients of the balance equations. These are 1 and 1 and 1. The reactants always go negative because they are going to react and disappear. The products always go positive. And then we'll have an equation for the Ka, for the equilibrium, and we can solve for x. In this case, this is 5 times 10 to the minus 2. And again, to do this analysis, it's best to think of it in terms of exponential notation. So this is a minus 2, this is to the minus 8, that's 10 to the 6. So it's 1,000,000 times larger. And therefore, in this case, the x can be dropped, and you can calculate the Ka by multiplying this number, sending this number along to here, multiplying it, and then taking the square root. So, and then you get the value of x, and the value of x corresponds to the concentration of hydrogen ions. So, from here. So then if you know the concentration of hydrogen ions, you take minus the logarithm of that, and you can calculate the pH. Okay. So let's get started on today's subject, which is going to be, again, acid-base titration for polyproduct. Poly means many, product means protons. So these are acids that contain more than one hydrogen, and they dissociate more than one hydrogen. Okay, then we're going to go into Lewis acids, formation of ion complex, and hydrated ions as acids, and the solubility of fluid. Sounds like a lot, but it's not much really. So let's again look at the titration curves for polyproduct ions. That means that when we look at titration curves, we're going to see the following. Here we have a base. So here we're starting with calcium carbonate, and we are reacting it with H plus or hydrogen ions to form bicarbonate in the first step. The second reaction is going to be bicarbonate reacting with more H plus to produce carbonic acid. So in this case, the analyte is carbonate. The titrant is a strong acid. So it's still an acid-base reaction. So in the first endpoint is going to be when we have transformed all the carbonate into bicarbonate, HCO3 minus. And that is, let me switch to a green color. So this is this point here. And this point, we have only, technically speaking, only bicarbonate. So we have added enough acid for this reaction to go in one way. The reaction doesn't go in one way, actually. It goes in both ways. It's an equilibrium. You can tell it from here. It's an equilibrium. But we're going to formally say that we have added enough acid here to neutralize or to protonate, fully protonate the carbonate. Of course, this is going to be an equilibrium, so it's not going to be in practice fully protonated, but that still is considered the endpoint. As you can see, when you look at the pH versus volume of titrant, you can see there's an inflection point. The inflection point is when a curve switches from pointing, in this case, downwards. So this is a curve that points downward, and it's concave towards the bottom, and turns into concave towards the top. This one, this point here is called the inflection point. So let me put it in orange here. That's the inflection point, and that's the equivalence point. That's when you're doing titration, and you can see that the concavity of the curve goes from pointing down to pointing up. then you can say that you have reached an inflection point. And those are the ones here. In simpler terms, it will be, if this will be a hill, this will be kind of a precipice. There's a precipice here, and there's another precipice here. So if you will be walking this way, you're going to find a very steep drop. And here's a second very steep drop. Those are the endpoints. So what you're going to see also is going to be the midpoints, and the midpoint is here. The other midpoint will be right here. Again, this is halfway through the addition of acid to reach the first endpoint. So halfway through, 1/2 and 1/2 on this side. Halfway through, you have the first pKa, and this will be the second pKa. So remember that we're looking at pH, so we're looking from the acidic side of the equation, or the acidic point of view. So these halfway points are always pKa. Okay. So, and so this is going to be, this is something important too. So this equilibrium here is KB, and this is KB. So there are two, and they correspond to, no, I cannot write outside the slide. They correspond to Ka. And this is Ka1 from the acid side. This will be the first dissociation of the acid, and this is the second dissociation of the acid. So for polyprotic acids, the 1 and 2 are with respect to the acid dissociation. So this is pKa1, and this one is pKa2. So they come in the reverse order because we're going in the reverse order in terms of pH. We're going from basic to acidic. Okay, so please interrupt me if you have any questions or any comments or anything that needs to be clarified. You know, you're being awful quiet. I'm sure that there are a lot of people that have questions, so please do ask. So otherwise, I'll have to change my approach to be able to conduct class if you're not participating.
I actually have a question.
Great, thank you.
So why do we only use pKa rather than pKb?
No, we can use pKb, but the reason that these correspond to the pKa, let me see if I can make a line or a different color. Let me just make it, let's make it orange. So good question. So here we're looking at we're looking at these 2 points, correct? And this is pH. So that means that the values that we have here are with respect to the acidity, and that corresponds to the pKa. If we switch this scale to, instead of plotting pH, we plot POH instead, we'll get rid of that and plot POH, then these values are going to be the pKb's.
Oh, okay. I see.
So it's just because we're using the pH scale. Remember that pH plus POH is equal to 14, and so is pKa plus pKb has to be equal to 14. So it's just the fact that we're using pH that we're seeing. We can say that these points, the y-axis is going to reflect the pKa. But if we'll switch to POH, then those axes, the values of those POHs at those points, then they reflect the pKb.
Okay, thank you.
You're welcome. Thank you for your question. Great, so that means that we have to stop the video, and so they don't become cumbersome to watch. And I've noticed that you are not watching that many videos. I hope you would be. Let me stop recording.